So I wanted to conclude yesterday's talk by telling you what we can deduce from the convergence of the clock process of the random hopping dynamics of the pace spin SK model for the two-time correlation function. So I don't remember exactly what I wrote on the board, but let me give you the definition of our two-time correlation function. Given delta positive, let an delta of TW and T be the event that the overlap R, N, between the process at time CNTW and at time CNTW plus T is larger than 1 minus delta. So to say that the overlap between two spin configurations is large is the same as saying that the distance, the Hamming distance between these two things, is smaller than delta n over 2. And the two-time correlation function we will choose, I'll call it pi tilde, is simply the probability of this event, starting in our initial distribution. So it is not the two-time correlation function we use in the random hopping dynamics of the REM. And I told you why yesterday, because we saw that when a trajectory of the process crosses a region where there is at least one very deep trap, then we know that it will meet not just one deep trap, but it will hit at least finite number of them in a very short time interval, so in a very small time compared to our theta n. So it is not true that the process in a given time interval spends all its time on just one point, because it will visit inside one of these balls several points that will contribute to, we saw yesterday, contribute to the clock. And then these regions are far apart from each other and uncorrelated, statistically uncorrelated, which led to the convergence of the blocked clock process. So for this two-time correlation function, we have that under the assumptions of yesterday's theorem, for all delta in 0, 1, all TW and T positive, the limit as n goes to infinity of this quantity is the arcsine law of parameter alpha epsilon. So under the same conditions on epsilon and beta as in yesterday's theorem, in this domain dp that depends on the parameter p that I wrote and won't write again today. And this is true almost surely in the random environment. So let me just tell you one little aspect of this proof. So just a hint. So we would like to bring ourselves back to the event that gives rise to the arcsine law distribution function, which is the event that the range of the blocked clock does not intersect the time interval TW plus T. So take the event AN and write it as AN intersected with E, union AN, intersected with E complement. So let us look at this event. What is E complement? E complement is the event that there is a point in the range of the blocked clock process that falls inside our interval. So let me write this for the limiting object. So let me call R, B, the range of the limiting clock process. So there's no n because I'm passing to the limit. So for the limiting object, the probability that of E complement is the probability that there is a point of the range falling inside the interval tw plus t. So that tells me that there exists a u such that the blocked clock process at u belongs to this interval. But we saw yesterday that this limiting object is a stable subordinator. So the range of a stable subordinator we know is a perfect set, which means that there is no isolated point. So if I can find one point in the range, then it implies that there are 2 points, u different than u prime, such that both SBu and SB of u prime belongs to this interval. But now we proved that the rescale clock process converges to the stable subordinator in the limit in the J1 topology. So this implies that there is a converging sequence SNU that goes to SNB, and similarly, so this converges, and similarly SNB of u prime that converges to SB of u prime. So for all n large enough, these two also are in the range. And here we use that every jump in the limiting process has a matching jump in the converging process for all large enough n. And we can do this because we work in the J1 topology. Now we remember what was SNB. It was the sum from 1 equals 1 to a n t divided by theta n, because we made blocks of increments z and I. So this is here a u now. And we have the same object here with a u prime. So this tells us that between those two visits in the range, the jump chain took at least, so the jump chain took at least a n u minus u prime jumps, steps. Now this is exponentially large, and we know that if the jump chain starts in one of these deep traps here, and you wait an exponentially large time, then you know that it will go very far away from this ball where it was stuck in. And essentially, it will go as far as it can. And we also know that the simple random walk does not revisit points in times shorter than exponentially large. So this tells us that this event is empty, has probability that goes to 0. And we deal with this event in a little bit in the same way. So this event is the one you want. And you still have to show that if you exit the ball, but it is essentially the same argument, if you exit the ball a little bit too far, then you never re-enter it. So the only event that really contributes to the event A delta is the event E. But as you see, it takes a little bit more than just convergence of the clock. It takes a little bit of information about your chain, and it, above all, takes to have convergence of the clock in a strong topology. Otherwise, you can do nothing. So this, I think, was all I wanted to say about this. I wanted to just briefly, perhaps, answer Renato's question, which was, what about the SK model? So in the SK model, our result does not apply. You remember that my result was true for p larger than or equal to 3. And the idea is basically, the reason is basically this. So we saw yesterday that when you start your random walk J inside your hypercube, you and take A and T steps, then you sample a certain number of energy values inside your hypercube. And basically what happened is that when you look at the rescaled sequence of these energies, the delta H along your sequence, this thing converges to a Poisson point process. So this is the, what makes really the entire problem works. And so the ancestor of this work on the P-spin SK model is a joint work with Gayrard, Ben-Arous, and Alexei Kuptsov, where we wondered what would happen if we, instead of sampling here these points with a random walk, we would just do it by sampling independent points, so Bernoulli trials, by Bernoulli trials with probability 2 to the epsilon n over 2 to the n. So here we have a walk of length 2 to the epsilon n, and then you get a cloud of size 2 to the epsilon n, but it's a little bit simple because if you sample your points at random, the structure is, of course, a little bit less correlated. And what we could prove is that if, so this, for the SK model, so let us say exponential minus beta h with some proper rescaling, it does converge to a Poisson point process u to the minus alpha du. But if and only if this epsilon here is little o of 1. So this means that this universality behavior that comes from the Poisson point process, it is valid in the SK model, but on timescales that are shorter than the exponential timescales on which we studied our model so far. Of course, you will say, well, why did you study your model on timescales an that are of the form 2 to the epsilon n? You can study it on shorter timescales, so epsilon goes to 0. So timescale shorter than this means that you have your alpha that goes to 0. Now, a subordinator with alpha 0 does not exist. So the limit cannot be a stable subordinator anymore. However, this problem has been solved in the literature on stochastic processes. It goes back to Kasahara in the 80s. What you do is that you rescale. Well, they say that they normalize the process in a nonlinear way. So you take the power alpha of your clock process, and this s to the alpha now converges to what we call an extremal process. An extremal process is a function of the points of the Poisson point. So we saw that a stable subordinator can be written as the sum over the points psi k for all k smaller than t of a Poisson point process, so where these points tk, xik are a Poisson point process, then an extremal process can be expressed as the sup over OK such that tk is smaller than t of xik. So actually, you can just use all we did, because all we have to prove is the convergence of the induced Poisson point process. And then instead of taking the mapping that maps the points into their sums, then you take the mapping that maps the points into the sup. It's just a different mapping. And doing this, you can prove that the normalized clock process with this nonlinear normalization converges to an extremal process, almost surely in the random environment for the SK model. So the first result on this, this first result on this convergence to an extremal process for the SK model was by Benarous and Honor-Gun. And they obtained this convergence in law with respect to the random environment. And using these techniques, I proved this result. It's a joint work with Adela Jreda, who was my PhD student, and Anton Bouvier. And we proved that this result is true almost surely in the random environment. There's a last little thing I wanted to say, is that, of course, you will tell me then there's still one point that you didn't talk about. It's alpha equals 1, the other extremity of the interval alpha 0, 1. And here also, we know how to proceed. So alpha equals 1, you will say formally, is just a straight line, because a subordinator with alpha 1, you just think it's a straight line. So it's not a subordinator because it doesn't satisfy the condition that the infimum of 1 and x d nu is finite. This condition, if alpha is 1, is violated. But of course, Levy's representation of, Ito's representation of Levy processes tells you how to manage with this case. And what it tells you to do is that you have to subtract here to this sum the explosion created by the small jumps here. This is called a compensated Levy process. So you subtract from this term the sum of the small terms that create an explosion. And then you prove the convergence of the clock to this compensated Levy process. And this is a result that I am just finished with Lisa Hartung, who is a lecturer in Courant Institute. So this is all I will say about the random hopping dynamics of these mean field models. And today, I will tell you what we can prove for metropolis dynamics. Metropolis dynamics was, when I started working on this problem with Benarous and Bouvier a long time ago now, this is the dynamics we wanted to study. We started headstrong on this, and we were totally stuck because it's much more difficult than this random hopping dynamics. At the same time, no physical system in the nature that you can observe behave like random hopping dynamics, because it is not true that the process evolves independently of its random environment. So to go to a more realistic setting, we really have to turn to metropolis. So let me give you the definition. And because the dynamics is more complicated, then of course we have to revert to the simpler model. So we go back to the REM. So metropolis dynamics of the RAM is a Markov jump process. So it's a continuous time Markov jump process on the hypercube Vn. I don't define it, we know this, with rates lambda n of x and y that are proportional to the exponential of minus beta times the difference between the energy at the arrival point, hy, minus the energy at the starting point, h and x. And this is if h and y is larger than or equal to h and x. So in directions of increasing energies, and it jumps at the constant rate 1 to all directions, all nearest neighbors of lower energy. And this is if x and y form an edge of the cube, and the rates are 0 else. So we see that these rates favor jumps that decrease the energy, because in upgoing directions, the rates are exponentially small, while they are 1 in downgoing directions. So let me give you the result for the correlation function, so I'm sure that I don't finish the class without stating it. So we have to choose the initial distribution. We will start from the uniform distribution on Vn. I call it mu n. We must choose the time scale. So given an parameter, epsilon in 0, 1, I will let a temperature, beta positive. We let Cn be such that 2 to the epsilon n, the probability that tau n x is larger than Cn equals 1. So the notation tau is, as usual, where should I write it? So this is the Boltzmann weight. So this is the definition of intermediate timescales. It's a little bit less general, but I wanted to simplify the notation a little bit. And the two-time correlation function that we will consider is the probability. I will call it pi hat. That starting in mu, the process xn is at the same state at the two time points Cn tw and Cn tw plus t. So we do not ask that the process does not jump into the time interval, because as we will see, this is not true again. But we ask that it is in the same state at these two extremities of the time interval. And as yesterday and the day before, I will write beta c of epsilon for the quantity 2 epsilon log square root 2 epsilon log 2. And alpha of epsilon is the ratio of beta c of epsilon to beta. Then what we can prove is that for all epsilon in 0, 1 and all beta larger than beta c of epsilon, for all tw and t positive, this two-time correlation function converges to the arcsine law with parameter alpha of epsilon at tw and tw plus t. And this is true P almost surely in the random environment. So this is the same result as we obtained in the random hopping dynamics of the random energy model under exactly the same conditions on our time scales and temperature parameter, and almost surely in the random environment. So the only set of time scales that I've left out are the time scales that are extremo or very close to extremo, where we saw that in the random hopping dynamics, this result was true in probability before the extremo time scale where the picture changed completely. For the metropolis dynamics, I have no idea what is the result on extreme scale. Okay, so now let us see, try and understand how we can prove this and why it is, again, true that, that the behavior is that of the REM-like trap model. So let us go back to the jump chain and holding time description of our process. And so we saw that when the process is, so when xn, the process xn is at x, it waits there, it waits an exponential time of mean value, I'll call it lambda minus 1 of x, where lambda n of x is the sum of the holding times, lambda n of x and y, over all nearest neighbors y of x. This is the diagonal of the infinitesimal generator matrix. And then it jumps according to its jump chain, J and I, which is the discrete time Markov chain with one-step transitions, little p of x and y, given by the ratio of the rate, lambda n of x and y, to the parameter lambda n of x. So we see that unlike in the random hopping dynamics where the jump chain was the simple random walk on the hypercube, the jump chain now, the trajectories of the jump chain now depend on the random environment. And it is biased against going upwards in the random environment. This we can express explicitly. So if you want, I'll just write it. So it is the exponential of minus beta, the maximum of h and x and h and y, divided by the sum over all nearest neighbors y of x of this quantity. So just do the plugin and check that you get this quantity. So to get some intuition about the behavior of this walk, I will show you pictures. Turn it on. Yes. Good. Thanks. So this is what I just wrote. So from this one-step transition probabilities, we see that when it is at local maximum, the process will hop, the jump chain here, will hop with a uniform probability in all directions that go downwards. So that's picture A. It has the same probability to jump left or to jump right. When it is at a local minimum the process, the jump chain, is more likely to exit through the lowest saddle, the saddle of lowest energy, because it's where this little probability here is the largest. And when two neighboring local minima are separated by a low barrier of energy, but surrounded by very high energy barriers, then the chain will hop back and forth between those two minima, and it will stay trapped there a very long time until at some random time it escapes. More generically, the process will spend very long periods of time trapped in the local valleys of the random energy landscape. How long, depending on the height of the lowest mountain pass through which it must cross in order to exit these valleys. So this type of behavior is typical of what is called metastability. To understand it, we must understand the valley structure of the random energy landscape. And this for us means look at the level set of our random energy landscape. So questions on the level sets of the RAM are questions on side percolation on the hypercube. So I will say that a vertex x is occupied if the Boltzmann weight at x, exponential minus beta h, is larger than some threshold function un. And I will choose un in such a way that a vertex is occupied with a probability 1 to the n to the power c, 1 over n to the power c. Now, instead of varying un, I will vary my parameter c. So we see that when we vary c from plus infinity to 0, this probability here increases from 0 to 1, which means that the set of occupied vertices increases from the empty set to the entire hypercube. What we know is that the nature of this set of occupied vertices changes completely at the critical value 1. If c is a little bit larger than 1, then Vn breaks into an exponentially large number of small disjoint connected components that I'll call C and L. We have about 2 to the n over n to the c such components. While in the complement, the set of non-occupied vertices forms a totally connected giant component. Now, this is in contrast with the case where c is slightly smaller than 1, when a giant connected component suddenly emerges that engulfs of the order of 2 to the n over n occupied vertices in the landscape, and it becomes bigger and bigger as c becomes smaller and smaller. So quite clearly, so I will now call such a set Vn a percolation cloud, and quite clearly for us, the local valleys of our random energy landscape will be located inside the small components before criticality. So to give you an idea of what the picture we have in mind, I have made this picture of a percolation cloud right before criticality. So the non-occupied vertices are in white. They form a totally connected giant component. It is this white soup in which the other components are. And the occupied vertices are in gray. So they are either isolated vertices. We have lots and lots of those. Or they form small connected components. So if we now attach our energies, you must think that inside these gray components, you have valleys. And inside the white one, well, we must keep in mind that the Hamiltonian of the RAM is a symmetric process. So if I change h into minus h, then I get a process with the same distribution. So this means that I have a similar percolation cloud disjoint from the cloud, the gray cloud here, but that will contain energies that are slightly larger. So that contains, instead of valleys, contains the hills or mountains of the landscape. So we have two clouds, two percolation clouds. One contains the valleys, the other one contains the mountain. And in between them, we have this white soup in which they swim. Now, the size of this white totally connected giant component contains only energies that are tiny fluctuations of the Hamiltonian, and tiny fluctuations means energies of the size square root a constant n log n, while the deepest, the extremes of inside the valleys, they are of order n. So at the white vertices, the energies are tiny quantities of the order square root n log n. Okay, so what is the heuristics for the dynamics of the jump chain in this landscape? Well, the jump chain here, a trajectory of the jump chain is in red. When it enters one such valley, then it stays trapped there a very long time. How long, depending on the characteristics of the random landscape inside that valley, until a random time, exponential random time, at which it will suddenly escape and then quickly travel to another valley, where it again will stay a very long time, and so on and so forth. So what we see is a sequence of slow motions, when the chain is trapped inside these local valleys, and quick motions between the valleys. So when we examine this trapping times inside the valleys more closely, what we get is that the extreme accessible trapping time, so you remember that we, in principle, think that this trajectory has length an. So the deepest traps, valleys where you stay trapped, I'll call them the extreme accessible traps, extreme accessible valleys. And they have trapping times, extreme accessible trapping times in valleys. They are carried by edges, xy, whose distribution is exponential. And mean time is proportional to the minimum of tau n x and tau n y. So this is very long. And these trapping times, they obey a sequential regular variation condition. So if I look at trajectories of length an and choose the scale bn in such a way that, this minimum is larger than bn is 1, then the same quantity behaves like, u to the minus alpha over 2. So we see that the trapping time is in the valleys is exponentially long. It is a random variable that is exponentially long. And it has a similar kind of regular variation behavior as we saw for the random hopping dynamics of the REM. So this is for the jump chain. It is not for the dynamics xn. So in the random hopping dynamics, the jump chain was just a simple random walk, and now we see that we have a process that has exactly the same feature as an aging process itself. So it doesn't look a very good idea to work with this jump chain because it is as difficult as the process xn itself. Still, we can have a look at what is its mixing time, because this was also a key ingredient for the study of the clock. So let me tell you what is the mixing time of this process. So is there a question? No, we can. There's one more, but I will show it later. Later, yes. So I'll call Kn of x the inverse of the spectral gap of metropolis dynamics, and I'll call Kn of j the inverse of the spectral gap of the chain Jn. So we know that bounds on the inverse of the spectral gap give us bound on the total variation distance to the stationary distribution of the process. So what we know, and this is a result of Luis Renato Fontes and co-authors, is that for all beta positive, 1 over n, the log of Kn of x, converges as n diverges to beta c of 1, p almost surely. So this tells us that the mixing time of the process is of the order exponential n beta c of 1. And the idea behind this is that when the process has found the deepest trap in the landscape, which is a trap of order exponential n beta c, then it will be equilibrated. If we now look at this process Knj, then using exactly the same kind of proof, what we can show is that now the jump chain J, K of J, this chain becomes equilibrated when it has found the edge in the random environment that carries the deepest valley. So the mixing time of the jump chain is exponentially large, exponential of the order exponential n beta c a half. So we see that it is the same of the order of magnitude as the mixing time of the process xn itself, and so it really sounds hopeless to apply the techniques that we have seen so far, because we have to replace a chain that was a simple random walk mixing in n square step, independent of the random environment, by another chain that has exactly the same behavior as the process xn itself, with just slightly changed parameter. So we really have to rethink our strategy a little bit, and this is what I am going to explain to you now. Perhaps you remember that in the first lecture, I told you when introducing the jump chain and holding time description of the process that we could give this idea a slightly different twist. So I'm now going to introduce what I'll call a continuous time clock. So instead of writing metropolis dynamics as the time change of its jump chain, I now want to write it as the time change of another process that I'll call the exploration process, YNT, which is another continuous time Markov jump process with rates lambda tilde, which I'll choose in such a way that the process Yn has the same jump chain as the process Xn. So this means that so you remember that this definition of little p, it is the ratio of lambda n of x and y to lambda n of x. So this is little p. So if I want my process Yn to have the same trajectories as the process Xn, then I need the little p to be the same for the two processes. So I need this to be equal to lambda n of x and y tilde divided by lambda tilde n of x. And this is, so I won't write it down. The lambdas with just one variable are the sums of the rates over the nearest neighbor y's of x. So I'll ask Yn to obey this relation. Then my two processes, x and y, are linked by the relation xn of t equals yn at some time change. Let me call it S tilde inverse. This arrow here is denotes the left continuous generalized inverse of the process Sn. And S tilde is what I call the continuous time clock. It is given by the integral from 0 to t of lambda n of Yns. Lambda tilde, minus 1, lambda tilde n of Yns ds. So you can easily check this relation. So, so now the idea is that I have a lot of freedom to choose my process Yn. So I will try to choose the process Yn in a way that I can use my techniques as easily as possible. So the first idea that comes to mind is I want a process Yn that has an invariance measure given by the uniform measure. This would make me very happy because a uniform measure is the simplest thing we can think of. So how to do this is easy. So the first idea, choose Yn such that its invariant measure is the uniform measure. So I'll use that. We know that metropolis dynamics is reversible with respect to Gibbs measure. This means that tau n x lambda n of x and y equals tau n y lambda n of y and x. So if I want to achieve this, then it is enough for me to take lambda tilde n of x and y to be the left-hand side of this equation. So if I do that, my new process Yn is reversible with respect to the uniform distribution. And if I plug this choice into this definition of S tilde, I then get the nice quantity integral from 0 to t of tau n y and s ds. at this point, I would like to say that this idea is an old idea in probability theory. I myself learned it in papers of Barlow and Deutschel, papers on random conductance models, where they have similar kind of problems. So what does this time change do? What we do here is that, so we saw that the trajectories of the process y and x are the same as before. So this y chain, it follows the same red trajectory as we saw before. It enters the valleys and just does as the jump chain, except that it travels along these trajectories at a different speed. And it travels at a speed chosen in such a way that essentially it goes constant. So when it goes at distance 1, in time 1. So when it enters these valleys, it is speeded up, and then it slows down, and it continues moving essentially at a constant rate. So in random conductance model, for those of you who are familiar with this, it's called the variable speed random walk. So the time change is adjusted so that in valleys where the jump chain would spend a lot of time, it is speeded up and then it goes through just smoothly. And that's the basic idea. So now the problem with this idea is that, as I told you before, because of the symmetry of the Hamiltonian, we have valleys, but we also have mountains. Well, we had this picture with all the little valleys, and so there was the white part, which was just tiny fluctuations of the Hamiltonian. Then we have valleys, but then we also have our mountains here. Okay, so that's the bulbs. This is the picture of a bulb. And then we have the same symmetric random cloud that contains mountains, these things. So the problem with this choice is that, in fact, if we calculate its mixing time, so if we calculate the inverse of the spectral gap, of y, so let me call it ky. Well, it's limit of the log 1 over n of ky. It is exactly the same, unfortunately, as the jump chain itself. And this is because when the process is slowed down, is speeded up in valleys, it is slowed down across the mountains. And then it is slowed down in the same proportion. So you keep having this problem that the spectral gap is absolutely huge. So, of course, there are several ways to deal with this. And the first of all is that, of course, this tip of the mountains, and from the point of view of statistical mechanics, they are totally meaningless objects, and they are there a bit by accident. So you can just slice them off if you want, or find ways to try to say, OK, this doesn't matter much. But there is a nice way to proceed, which is the following, and which I learned in a paper by Czerny and Wasmer. So the better idea is to introduce another scale, eta n, and set lambda tilde to be the maximum of this scale n tau n x times lambda n of x and y. So what does this do? So if tau is large, so a large Boltzmann weight is a deep valley, then so say think of this as being quite small, then this will be bigger, and we get the same choice as here. So we didn't change anything when we cross the deep valleys. So we speed up the process as it goes across the deep valley. But now, when it hits the mountains, then this becomes small. And when this is small, then you don't change your speed except by a constant in proportion to eta n. So this process essentially is speeded up as it goes across the valley, but it's not changed elsewhere. Of course, I have a different. I don't have my ideal uniform distribution, but the invariant measure. The invariant measure is not too bad. So let me write it. I'll call it by nx. It is given by the minimum of tau nx and tau ny divided by the sum over Ox in Vn of the same quantity. So this is if eta n is a positive sequence, and otherwise it is just a uniform measure. So, so basically, this will remain close to the uniform measure if eta is small enough. So we are quite happy. And what does the spectral gap now become? So the spectral gap. So this was with the first choice. So this second. So with the first choice, we had this behavior, and with the second choice, ky of n behaves like the inverse of eta. So now we have to play a game. We want eta to be small for the pi measure to look like the invariant measure, but we want it to be not too large so that our mixing time will remain small enough. So this is the idea, and the clock that we obtained. So let me erase this because we now don't need it. And the clock that we obtained doing this is simply the integral from 0 to t of the maximum of eta n and tau n at y n s ds. Okay. So now we of course want to apply our techniques because we are in a good position to do that, and use the sufficient conditions that I gave you yesterday, Duret and Resnick sufficient conditions to deduce convergence of this clock. The conditions I gave you yesterday are for discrete time partial sum processes. Here we have a continuous clock, but of course we will introduce blocks and turn this clock, this continuous time clock, into a discrete time clock by blocking. So given a sequence theta n as yesterday, I'll let kn of t be the ratio of a and t over theta n. So let me call the clock without the tilde let the clock without the S tilde be the rescaled clock process on timescale Cn and auxiliary timescale An. This is, so the question as we, is the same as we ask ourselves each day is what are the scalings An and Cn that make this process converge? So I'll first introduce a sequence theta n and use it to split this sum into blocks and define the blocked clock process as Bn as the sum from 1 to knt of increments z and I that are given by the integral from theta I minus 1 to theta I of these quantities. And I'll now apply Direct and Resnick theorem to this object. So we won't go through the sequence of arguments that we saw yesterday. The idea is to use a mixing condition to reduce the conditions that we obtain in Direct and Resnick's condition to, on the one side, this mixing condition, and on the other side, conditions that are of the form of laws of large numbers in the random environment. So let me just state this condition and the theorem that goes with. So the first is the mixing condition. It states that there exists a sequence, kappa n, and a decreasing sequence rho n, such that for all x and y in the landscape and for all t positive, the probability that's starting in x, this p probability is the law of the process y. The probability to find y at time t plus kappa n in state y minus pi n y. Pi n is this invariant measure, is smaller than rho n pi n y. So this is our first condition, C1. Then the next two conditions are of the forms of strong laws of large numbers. Let me define the quantity nu t n of u infinity as kn of t times the sum over all x in Vn of pi n x, the invariant measure, times, so I'll tell you what is q, where q un is the tail probability starting in our initial distribution mu of the increment z and I. So the first condition, or rather the second condition, C2, is that this quantity converges to the tail of a measure nu for all u positive, where this measure nu, I don't repeat it, obeys the conditions of Direct and Resnick's theorem. So this is the first condition, and the second condition of condition of the form of the strong law of large numbers. So let me call it C2a and C2b. Is that the quantity defined in the same way, but replacing q by q squared goes to 0 for all u positive. So we saw these two quantities coming yesterday, and there was a third condition. Let me call it A3 because it was our third condition of yesterday. This is the condition that is needed to guarantee that the sum of the small jumps, when you sum the points of your point process, is washed out in the limits. It's always in a condition of the same form, so I won't write it down. So we have to check these 4 conditions. And the theorem then states that for all sequences, so I have several sequences. I have AN, CN, theta n, let's say kappa n first, theta n. My theta I know must be larger than kappa and smaller than AN. So for all sequences such that my conditions are verified, C1, C2a, and C2b, and A3. So for all sequences for which these conditions are verified, either P almost surely in the random environment or in P probability, then with respect to the same convergence mode, this sequence of processes, Sn, converges to converges in D in the J1 topology to a subordinator where S is a subordinator with triple 0, 0 nu. So we saw that yesterday. So this is what you get when you apply Duret and Resnick's techniques and use a mixing condition to reduce, as we saw yesterday, the Duret and Resnick's condition to laws of large numbers. And now we have to wait. Yes, sorry, there's a B. This is the block clock process. For the to make sense of writing a J1 convergence, you need the discrete object. So, of course. So thank you for observing. Okay, so we have a set of sufficient conditions that we want to check in order to prove convergence of our block clock process. So I will tell you the result. So what you see is that I already told you that this condition, we know how to satisfy it because we chose the process Yn, inserting this parameter eta n. And we know that varying eta n, we will vary. We have some control on the mixing time of the process. So we are not worried about this. It's totally under control. And the most difficult part is to understand the convergence of this new n quantity here that gives us the Levy measure of our limiting subordinator. So this, in all the examples that I have discussed in these lectures, has always been the hardest part. So we have to state the convergence result for the clock. We have to choose several quantities, all our sequences. So I will first tell you how we choose the sequence eta. So let me introduce first constant C star that I'll take larger than 1 plus log 4. So it is a small constant. And let R star of n be the sequence such that n C star times the probability that tau n x is larger than R star is 1. So if we explicitly work out this sequence, we get that explicitly that R star n is of the form exponential times beta square root 2 C star n log n times 1 plus little o of 1. So this is, so this C star is just a bit above 1. So we are just below criticality in our percolation cloud. And R star is the typical size of the fluctuations of the Hamiltonian inside the totally connected giant component. So it's just a little bit the size of the largest fluctuations in this white part. So let me take now eta n to be the inverse of R star n. So it is a rather small sequence. And then condition C1 is verified, I'll tell you without proof, is verified with kappa n equals n4 2 times R star n P almost surely. So this is our mixing time quantity. Now, having the mixing time, I still have to choose. So this gives me the mixing time. Now I have to choose the sequence AN. This is going to be a little more involved than in the random hopping dynamics. So I will write my sequence AN in the form 2 to the epsilon n divided by a sequence Bn, and I am now going to define this sequence Bn. To do it, I would like to show you the last picture. Yes. So on the last picture, I have placed the blue dots that we had on the very first picture I showed you. So everything is as before, but I represented by blue dots the set of vertices in the landscape that carry Boltzmann weights that are of the order of Cn. So of the size exponential n beta beta c. So this is, again, a random cloud, a percolation cloud according to my definition, but now with a density that is extremely small, exponentially small, compared to the density of our gray percolation cloud. So I used to call it a Poisson cloud because it's a very rare cloud. So if we believe that the heuristics is the same as in the random hopping dynamics, the leading contribution to the clock will come from the visit of the red trajectories here to the blue dots. So our process Y travels along the same red trajectories here as the jump chain at a different speed, but the same trajectories. And along it, it will pick these blue dots. And the heuristic picture is that the leading contribution to the clock must come from the visit to that point. So I'll call Tn this Poisson cloud. I also call it the top because it contains the very large Boltzmann weights. So we can turn off the picture. It is just because I thought it was nicer to have the picture of the cloud Tn than a definition of it. So the definition now of the sequence Bn depends on that Tn cloud. It is defined as the sum over all vertices in Tn of the local times at x in times interval of length theta n to the power alpha of epsilon with a normalization 1 over theta n pi n, the invariant mass of the set Tn. So this definition looks a little bit ugly, but I will give you right after the behavior of the sequence Bn. So what the theorem tells us, now that we have all our sequences, is that given epsilon in 0, 1, I still have to tell you how I choose my theta n. Let it be such that the log of theta n is much smaller than n. So our blocks are much smaller than exponentially large and larger than the log of r star n times some constant. So we still have quite a lot of freedom to choose our theta n blocks because this is of the order of square root n log n, and this is n. Now, having chosen theta, let an and cn be, so an as here, and cn, I wrote it earlier. Let me just remind you. Cn is such that 2 to the epsilon times the probability that tau is larger than Cn equals 1. So B as we just defined. Then we have that for all epsilon in 0, 1 and beta larger than beta c, P almost surely in the random environment, the blocked clock, the sequence of blocked clock processes converges to a subordinator where S intermediate is in fact a stable subordinator of Levy triple 0, 0 nu and Levy measure nu equal to, with tau, u to the minus alpha, yes, without constant. Okay. So this choice of the process yn is quite efficient because we could prove convergence of the clock with still a lot of freedom of choice in our parameters. So this sequence Bn here is still a little bit mysterious. In the random hopping dynamics, the choice of an was just 2 to the epsilon n, and now we have this random correction. It's I wish I were able to say that this quantity converges to something, but I was not able to prove that. So what I can tell you is that, so under the assumptions of the theorem, you can find a probability space, a subset of our probability space that has full measure, and such that on that space, on omega prime, for all but a finite number of indices n, the sequence Bn is bounded above by n to some constant c plus times r star to the power 1 plus alpha of epsilon plus a little o of 1. And it is bounded below by n to some other constant c minus r star to the same power to the minus 1. So I don't have a very sharp upper and lower bound. But this anyway implies that the limit of the log of the sequence an as n goes to infinity divided by n is equal to epsilon, p most surely. So this sequence here, we must think reflects the fact that that your very deep minima have exit places that have tiny fluctuations in size, so the time you actually spend in your very deep minima does depend on this exit positions, and create some tiny perturbation on your time scale that in the, well, I don't have a very nice way to describe where it comes from. So when you want to prove this condition here, so let me write what the z here is. It's the maximum of eta n and tau x scaled by Cn minus 1 max, and that's the chain y s. And there is an integral missing. Yes. Yes. So this is the tail of the aggregated jumps inside the time interval theta I plus 1. So if the chain enters one of these blue dots there, in fact, when you want to control the tail, so you see your blue dots are still very far apart from each other. We are not in the pastebin picture. The very deep traps that contribute are really very far apart from each other. So there's only one blue trap that will contribute in each of these theta blocks. So when you hit one, there will be only one that contributes, but you may have many returns to that one trap. And this B term here, it is where it comes from. When you work out the distribution of this object, you have to take into account the local times at the deep sides that contribute in your set T. And OK, it gives you this, this quantity. So there is still, in the techniques to prove this convergence, the percolation picture that I showed is really important. So it comes into the techniques a lot. And so for this reason, you see there's still quite a distance from from solving metropolis dynamics in the P-spin-SK model, because here we don't have the picture of the level sets of the random energy landscape. This is something that is not yet understood. We could, in the random hopping dynamics, have a nice description of the valleys along a walk, but it is a different question from finding the picture of the level sets over the entire hypercube. So I think I will stop here because I've already used my time. Thank you.